today we're going to continue talking about magnetic fields around a current carrying wire. But we're going to focus on what happens to a magnetic field if a charge travels through that field. Let's just do a quick review of our right hand rule from last time. Remember, your thumb goes in the direction of the current and your fingers curve in the direction of the field. So which diagram below shows the correct magnetic field around our current carrying wire? So our thumb should be pointing to the left, and our fingers are going to curve in first and then out. So remember, in means X's, and out of the board on the bottom will be dots. So the answer should be C on this one. Let's try another one. So what direction is our magnetic field around our current carrying wire? So our wire is in the loop, so it's pointing to the left, and my fingers are going to curve out on the top, like I'm grabbing the loop, and in on the bottom. So dots on the outside, X's on the inside. So my answer should be D on this one. Okay, so let's talk about what happens to the magnetic force if we have a charge that's moving through our magnetic field. So last time we talked about the magnetic field around a wire that's carrying current. Today we're going to talk about the magnetic force acting on a charge moving through our magnetic field. So magnetic fields are observed to exert a force on a moving charge, but only if the charge is moving in the direction of its velocity. But only if the charge is moving and the direction of its velocity is perpendicular to the direction of the field. So what does that mean? So if we have our magnet here, and we have a charge that's moving through it, we see our velocity is going to the left, and our field is going up and down. So they create a 90-degree angle here between the field lines in red and the velocity in black. So the charge has to be moving perpendicular to the direction of the field. So we have an alternative right-hand rule that we use to determine the direction of the force on that charged particle. So again, we're going to use kind of, looks like a gun, but you have your fingers pointing outwards. So the thumb is going to represent the force acting on your charge. Your pointer finger is going to represent the direction of your charge's motion, so the current or the velocity. And then your fingers coming out to the side here are going to represent the direction of the field. So if I have my finger like the picture, thumb is upwards, finger points in the direction of velocity, the field points in the direction of the other fingers of your hand. So let's try an example here. So if we notice, the force on a negative charge is going to be the same in the same field, is going to act in the opposite direction. So if we have a positive charge, we can use our right hand rule. If we have a negative charge, you can either just change the direction. So it's going to be opposite the direction of the positive charge. So if our force is upwards for a positive, for a negative charge, it would be downwards. Or for a negative charge, you can use your left hand rule, whichever one you want to choose. So right hand should be positive, left hand will be negative, or you can just flip whatever you get for your right hand rule. So positive charges are what your right hand will show you. It's the opposite for a negative charge. So let's try an example here. So what is the direction of our force? Remember, the force is your thumb. On a proton, so a proton is positive, shown moving as to the right below. So my force is my thumb. My velocity is my pointer finger. So my velocity should be pointing to the right. And my field lines, which are represented with the dots, should be pointing out at the page. So I have my thumb now pointing downwards to get my fingers to point out and my pointer finger to point to the right. So my answer for this one should be D. My force is going to be downwards on that charge. So we would see the charge start to move downwards. So answer is D on this one. So let's try another one. What is the direction of the magnetic force on a proton? So proton, I can use my right hand, below. So remember, have it set up, thumb up, pointer finger out, fingers curved. So my velocity, my pointer finger, should be going downwards this time, but my field line should be pointing towards me. So my finger should be pointing back towards me. My pointer finger should be downwards with velocity, and so my thumb then is pointing to the left. So answer should be D on this one. So we'd see the charge kind of move in a curved pattern like this. D. Okay, so let's try this one. So now we're talking about an electron. So you can use your right hand rule, but you just choose the opposite answer. So I'm going to continue using my right hand. So my field line should be pointing outwards towards me. Okay. My velocity, my pointer finger, should be pointing downwards. And so my thumb points to the left. But remember, we're talking about a negative charge, so that's actually flipped. So answer should be A on this one. Now let's try it with your left hand. So if you take your left hand, my velocity is downwards, and my fingers are pointing towards me, and we see that my thumb is pointing towards the right. So answer would be A still. So either way works. You just got to remember, positive matches your right hand, opposite for a negative charge. Let's try another one here. So what is the direction of our force? So you have your hand set up. The field lines, which are your fingers, should be pointing out, so towards you. Our velocity says it's pointing, our middle finger is pointing in. So how does that work? We can't. Remember, they have to be perpendicular. So you can't both be pointing to the left and out with the same, doesn't work. So answer should be 0. There should be no force on this charge. Right? We can't change how our fingers are set up here. Velocity needs to be pointing in, but our fingers need to be pointing out. So that doesn't work. So that means they're not perpendicular to one another, and so there'd be no force acting on our electron. Let's try this one again. So what is the direction of the force on our electron? So remember, electron is negative, so I can use my right hand, I just got to change the sign. So my velocity, my pointer finger, should be pointing to the right, and I should be pointing out at me. This one's a little bit hard to do with my fingers. So pointing this way, and my finger is pointing towards me. So my force is going to be downwards, but remember it's electrons, so it's actually going to be upwards, opposite, or B. Let me try that with my left hand. So my pointer finger should be pointing to the right. My fingers, the field line, which are represented by these circles, should be pointing towards me, out. And so my thumb is upwards, and so my answer is going to be B for my electron. Okay, so number 6 wants to know what's the direction of a proton. So proton, I want to use my right hand. So my pointer finger, my velocity should be downwards, and my field line should be pointing outwards, and it's a little bit hard to turn my hand that way. So pointer finger is downwards, field is outwards, or into the page, so my thumb is pointing towards the right. So answer should be A on that one. So for these ones, you just got to remember what each finger is representing. So force upwards, velocity, your pointer finger, your field line, your field is your fingers. Just a second here, my slides are kind of working a little bit slow. So how can we actually quantify this? So we can find the direction using our right hand rule. Okay? But how do we know the actual magnitude of that force? So not only do our magnetic poles exert a force on each other, but the magnetic field will exert a force on a moving charge that's moving through that field. So if the charge is not moving, though, it's not going to feel that force. So a force on a moving charge is related to how much charge is there, what is the velocity, and then what is the strength of that magnetic field. So the equation here is what we're going to use. So F stands for force, measured in newtons. Q stands for our amount of charge, measured in coulombs. Velocity is V, measured in meters per second. And B is our magnetic field, measured in Teslas. So I'm going to draw that in so that you can kind of visualize that as well. So F is our force, measured in newtons. Q is going to be our charge, measured in coulombs, capital C. V is our velocity. So how fast is that charge moving? And B is our magnetic field, measured in Teslas. So we need to make sure when we're calculating with this equation that we are calculating with those units. So if we're not in those units, we got to convert. So let's try an example. So a proton is moving at a speed of 75,000 meters per second, horizontally to the right. So right tells us it should be a positive velocity. It enters a uniform magnetic field of 0.05 Tesla, which is directly vertically downwards. So it's telling us that they're perpendicular, so we're going to have a force. We want to find the direction and the magnitude of the force. So direction is going to be our right-hand rule. The magnitude of the force will be when we calculate. And it tells us the proton has this amount of charge. So let's try calculating first, and then we'll find the direction with our right-hand rule. So we're using our equation. Force equals our charge times velocity times our field. So my charge is my amount of charge for my proton, 1.6 times 10 to the negative 19th. Coulombs is the right unit. V stands for my velocity, so 75,000 meters per second, also right unit. And my magnetic field is my Teslas, 0.050. Teslas is the right unit. So I'm going to multiply those together to get my answer. And if I calculate, I get 6.0 times 10 to the negative 16th, and force is measured in newtons. So now I want to find my direction. So we're using the right-hand rule to do this. So it says my proton is moving horizontally to the right. So my proton, right-hand rule, so I should be pointing to the right. And my magnetic field is vertically downwards. Okay, so my lines are down, my finger is pointing to the right. So that means my field is going into the page. So we would a lot of times consider that going north. So you can write into the page or north would be acceptable. Let's try one more together. So now we're talking about an electron. So remember, electron is the opposite of your right-hand rule, or you can use your left hand. So an electron experiences an upward force of 2.8 times 10 to the negative 12th newtons when it's moving at a speed of 1.5 times 10 to the 6 meters per second towards the north. What is the direction and the magnitude of the magnetic field? So this time I'm solving for B, my magnitude of my magnetic field. But same equation. So force equals my charge times velocity times my field. I'm solving for B. My magnetic field is what I don't know. So my force is 2.8 times 10 to the negative 12. My charge is that of my electron. So I just want the magnitude so I can ignore the sign for a moment. My velocity says it's moving at 5.1 times 10 to the 6 meters per second. And I need to solve for B. So to get B by myself, that means I'm going to divide by both of these numbers, 1.6 times 10 to the negative 19th. And I'm also going to divide by my velocity, 5.1 times 10 to the 6. So make sure I divide by both of those. So my magnetic field strength is going to be 3.4 Teslas. So now let's find the direction of the magnetic field. So remember, magnetic field is represented by your fingers, your other fingers. And we're going to be opposite of whatever I get because we're talking about an electron. So it says my force is upwards. So my thumb should be pointing up. And my speed is moving north. So remember, north is considered into the page. And then my hand is pointing to the left. But remember, it's opposite for an electron. So my answer should be to the right. So it's 3.4 Teslas to the right. So when we say into the page, we think of that as north. Out of the page, we think of that as south.